architecture. HP and LCA for short.
That's right. And we're exploring what's called the highest Prestonian limit. It's really about the absolute theoretical ceiling of controlling a system, any system.
And the ambition here, it's huge. Our sources say the goal is to shift prediction, fundamentally shift it into definition.
Exactly. Think supervenient control. So the high-level goal, maybe terraforming Mars, stabilizing its climate, is simultaneously happening through actions at the lowest level, like direct molecular engineering on the ground.
Wow. Okay, that's spanning incredible scales. And it pulls together fields like, quantum chaos, phononic engineer.
Like systems dynamics, You need all of them working together.
So let's start big. Planetary scale. If you're, say, trying to terraform Mars, how do you mathematically manage that chaos? Introducing gases, changing the whole atmosphere?
Right, it's a massive intervention. And you can't use the standard Lyapunov exponent for that. That's for tiny infinitesimal errors growing. When you're dumping tons of greenhouse gases, the initial error or change is huge. So HP and LCA uses the finite size Lyapunov exponent, FSLE.
FSLE. So that specifically tracks how large disturbances evolve, like managing the planet's overall mood swings.
You could put it that way, yeah. It ensures those big control inputs, the terraforming agents, behave in a predictable or at least bounded way over time. Keeps things from going completely off the rails.
Okay, that handles the macroclimate stability. But then down at the quantum level, where you're doing this molecular engineering, that's noisy, right? How do you maintain control and coherence there?
That's where the quantum site comes in. It uses a protocol based on the quantum anti-butterfly effect.
Anti-butterfly, so the opposite of chaos.
In a sense, quantum chaos scrambles information. This protocol effectively runs the system's evolution forwards and backwards in time.
Like rewinding a tape.
Kind of. To see exactly how the information got scrambled by noise. By quantifying that, you can then actively reverse the scrambling. It's how you keep the quantum actions precise despite the environment.
Okay, so we have the math for the big picture with OFSLE and this anti-butterfly trick for the small scale. But what's the physical tool? How do you actually manipulate molecules?
That's phononic engineering, using sound particles. Phonons.
Sound, not light.
Exactly. The key advantage is deterministic phase control. With phonons, you can control their phase precisely, which gives you direct deterministic control over molecular interactions. Light-based photon systems, they always have an element of statistical randomness you have to fight. Phonons bypass that.
Incredible precision. And the mathematical instructions for that specific molecular work, like, building ammonia from Martian soil components.
That blueprint comes from the continuous time differential Lyapunov equation, the DLE.
The DLE.
Okay. It essentially gives you the complete statistical description of the quantum state you're aiming for. The control system then uses the phonon phase, guided by the DLE, to nudge the molecules into the desired configuration.
So you use things like acoustic metamaterials to focus this sound control.
Right. Acoustic metamaterials, phononic crystals. They shape and localize the phonon fields with sub-wavelength precision. That lets you do in situ synthesis, making what you need right there from local resources.
The way these mathematical frameworks link up from planetary climate down to atoms, it's amazing. But it brings up a huge question. We know how the system builds things, but what tells it what to build? What defines the ultimate goal, the purpose?
Now you're hitting the philosophical core of HP and LCA. It's a concept called downward causation.
Downward causation.
Yes. The highest Prestonian control, the ultimate input, isn't just data. It's non-reductive intent. The high-level desired outcome, like a successfully terraformed Mars, acts as an informational constraint on the system.